Hi everyone, I'm Luca Zanolini, and today, together with Roberto Saltini, we are going to give you an overview of our fast confirmation rule for the Ethereum consensus protocol. This is a joint work with Aditya, Francesco, and Chenyi. So let's start by answering this question: what is a confirmation rule? Before that, let me give you a quick definition that will be useful throughout the course of the presentation. What is a canonical chain? A canonical chain, very roughly speaking, is the chain that is followed by the honest validator, so the honest participants in the consensus protocol. For more technicality, is basically the output of the fork choice function, but let's just stick with the chain followed by the honest validator. Our fast confirmation rule is an algorithm that enables nodes that run this algorithm to identify blocks that will never leave the canonical chain, assuming good network conditions. Basically, this algorithm outputs whether a block is confirmed or not. And it satisfies these two properties. One is safety, meaning that if a block is confirmed by a validator at a given time, it will always remain in the canonical chain forever, basically. Moreover, we have also monotonicity, meaning that if a block B is confirmed at a given time, it will always remain as confirmed, meaning that if we confirm a block today, tomorrow it will remain confirmed. Sorry? Sorry, something is going on with the presentation. Okay, sorry. Today we will focus only on safety property, given that monotonicity actually requires some technicalities that are out of the scope for this overview. Okay, why do we need a fast confirmation rule in the first place? So today, the way to know whether a block will always be in the canonical chain is through finalization, right? The problem is that with the currently implemented protocol, finalization takes up to 13 minutes in the best case scenario, and for some kind of users, this might be too long to wait to get a confirmation in some sense. Moreover, we cannot really use block confirmations as we were used to do with proof of work, for example, where the more blocks are appended on top of a block, the higher was the likelihood that this block remained confirmed. Because in the current protocol, we have seen some attacks called balancing attacks, where the adversary could manipulate, in some sense, the view of honest validator, making them believe that they were participating in a chain. So in some sense, this might not be the real chain under this attack. So block confirmation doesn't really say anything about whether a block will always remain in the real canonical chain, in some sense. So with a fast confirmation rule, what does a fast confirmation rule give us? For sure, it gives us improvement on the user experience in Ethereum, because for having faster confirmation rule implies that small values transaction can, in some sense, don't have to wait for finality, but they can already immediately be assumed as confirmed, implying that they will eventually get finalized. Moreover, it reduces also risk trade, basically trade reversal, made by for exchanges that allow to optimistically trade immediately upon deposit. And moreover, it improves also reliability of some wallets. In particular, there are wallets that tell user that a transaction is already confirmed upon entering, upon including in the block. But as we said before, because of this possibility of a balancing attack, this doesn't really tell us anything meaningful. So having a fast confirmation rule can really improve also reliability of wallets in general. It's also useful for PBS in the sense that it provides block builders with an indication whether the block that they are building upon is actually not going to be reorged. So in some sense, this fast confirmation rule can give us more reliability and can help users that want faster confirmation time instead of having to wait finality. Before going into details of this confirmation rule, let me very quickly give you an overview of Gasper. This because Roberto will introduce some technical terms that it's better if we are all synchronized on that. Gasper is the name of the consensus protocol. This is a proof-of-stake protocol that can be seen as made by two sub-protocols. One is LMD Ghost, which is a synchronous consensus protocol that determines the canonical chain. And Casper is the finality gadget on top of this that finalizes blocks that are outputted by this LMD Ghost. Basically, it finalizes blocks on this canonical chain. The time unit in Gasper is a slot. A slot lasts 12 seconds. 32 slots define an epoch. For every epoch, the set of validators is partitioned in 32 disjoint committees. And at the beginning of a slot, a proposer is randomly selected from a committee, and it proposes a block on top of the canonical, on top of the head of the canonical chain. And the other validators in the committee will just cast a vote, ideally for the block that has just been proposed. How validators choose which is the head of the canonical chain? They do it through the fork choice function. Fork choice function selects all the latest messages ever cast by validators, and it chooses the heaviest chain in terms of stake that these messages carry. So for example, with this image, this is the canonical chain, and proposers will just append a block on top of B9, for example. One last thing, in case of a validator sending two conflicting votes for the same slot, we do not count these votes for determining the weight of this chain. So we discount equivocations. Now let's dig into the technicalities of the confirmation rule, and Roberto, thank you.
Thank you, Luca, for setting the stage with all the concepts we need to understand how the confirmation rule works. So let's start with some assumptions we rely on. The first one, we rely on the fact that votes sent by validators are received by other honest validators by the end of the slot. The second assumption is that we assume that there exists a maximum beta fraction of dishonest stake across any set of committees. So take any set of committees, we assume that maximum beta of the stake of this committee is dishonest, and 1 minus beta is for sure honest. Okay, as Luca mentioned, we cannot rely on chain depth at all. We do need to rely and look at the weight of the LMD Ghost votes. So how do we do this? Well, let's start by assuming this block B10 is canonical for now. For our example, we use beta 0.2, 20%. And then we assume also for simplicity that the weight of a committee is 100. Now, what we're going to require is S represents the support, the weight of LMD Ghost that goes towards block B11. We require that the S is larger than W multiplied by half plus beta. We'll see why. But just running through the examples, in our case, this means S of B11 more than 70, and we pick 71. We know that any other block for this slot that is conflicting with B11 has no more than, actually it has less than half W votes. So, which means less than 50, let's pick 49. What is the worst case scenario? Well, the worst case scenario is that beta of the stake equivocates. If beta of the stake equivocates, then 20, basically weight of 20 is subtracted from 71. We have 51 for B11 and 49 for anyone else. Well, B1 wins the fork choice. So yes, with this rule, we can say B1 is canonical. But are we done? No, we are not done. All we can say is B11 is canonical in this slot. We want to say B11 is canonical forever. And we can do that, but we see why we can't do that just right now. So what happens, for example, if we move to the next slot? Let's start with progress with our example. When we go to the next slot, the committee weight goes to 200. Every honest one votes for B13. These votes, 80, go also to B B11. Now we have B11 as a weight of 131, but what we need is higher. We need 200 multiplied by beta plus half. We need 140. So we're not quite there, and what does this mean? Is B still going to be canonical? Well, the answer is yes, it is. But in order to prove it, we need to do some clever trick. This clever trick is assuming that we somehow, for now, we know who is honest. So we are going to use this H. H represents the votes for B11 that are from honest validators. Bear with me, we'll go over this honest thing later. And J represents the validator, the stake in the committee that is honest. What you're going to require is that H of B11 is larger than half the total weight of the committee. Clearly, honest validators never equivocate. Clearly, this will make B11 win the fork choice. But we are going to work with something a bit more complex, which is this. We are going to require that H of B11 is larger than J, which is the honest committee, multiplied by half divided by 1 minus beta. We'll see why this matters. The thing is that this second condition implies the first one. Can show you by running, using our numbers, we get HB11 more than 50. We just pick 51 for now. So what happens when, okay, sorry, I forgot this. We define an indicator, P, for usefulness of the fraction of H over J, which in our case turns out to be around 0.63, which is larger than half divided by 1 minus beta. So what happens when we go to the next lot? Let's have a look. Okay, the committee increases to 200. The honest committee increases to 160. Now, everybody that is honest votes for B13. This weight goes to B11 as well. If you now calculate P, we have 131 over 160, which is roughly 0.81, which is larger than our target of 0.625. That's exactly what we wanted. As we showed before, this actually implies that the B11 is at least more than half of the possible votes. So B11 will be canonical. Now, for those who actually know intimately Gasper, they might ask, well, but when you cross the epoch, things are not exactly like that. But I show you that that's not a problem. So what happens when you cross the epoch is that it's possible you have a new validator set that is sampled, but it's possible that in the new slot, you have validators that have already voted before. So in this example, we assume that the honest committee only increases by X, some X of some sort. So in the new slot, 80, all the honest one will vote in support of B13. And because X stake is new, they have not voted before, so the support for B11 will increase by X. Now, if you calculate P, is 51 plus X over 80 plus X. Because X is added both above and below the line, and 51 is less than 80, we know this is larger than 51 over 80, which already shown is larger than our target. So what we have achieved, what we have shown is P, this indicator P, never decreases. So once it's higher than our target, which is half divided by 1 minus beta, we know B1 will be canonical forever. But now, how do we measure P? Well, lucky for us, if we use our initial fraction, which is S over W to be larger than half plus beta, actually this implies the threshold that we want for P. So we're left with one last thing. So basically what we have is that if you have this, the Q, which it's what we mean to be defined to be S on W, to be more than half plus beta, this implies that our threshold on P and that B11 will be canonical forever. One last thing, how do we assume that B10 was canonical? How do we solve the problem? That's very easy. We ask, the question is Q more than half plus beta for B11, then we go back to B10, to B9, until we get to the finalized block. So in terms of LMD cost, that's all we need in terms of confirmation rule. Things get a bit more complex when we add FFG Gaspar. So with FFG Gaspar, the fork choice gets a bit more complex. We start from the latest justified checkpoint, which is roughly the checkpoint that is ready to become finalized. We remove some blocks that are problematic, and then we apply the fork choice that Luke explained before to the remaining blocks. So what we need to do to ensure that B and some block B is canonical forever, we apply the rule that we saw before for LMD Ghost, and then we need to work out a series of conditions that ensure that B will never be filtered out by the effect of integrating LMD Ghost with Gaspar. This amounts to, in our case, we require that the checkpoint justified by block B is from the previous epoch. This ensures that in the current epoch, block B is not going to be filtered out. And then we have this more complex condition, which I'll break down soon, which ensures that B will not be filtered out in any future epoch as well. So what we're going to do in this condition, we look at the weight of FFG votes for the checkpoint of B. We remove the maximum amount of those votes that can be slashed, because perhaps they're Byzantine. So this corresponds to beta, the weight of the committee from the beginning of the slot to the current slot. And then we add the minimum amount of weight that will keep voting for the checkpoint of B, which is the 1 minus beta, the remaining weight between the next slot and the end of the slot. And we require this to be more than 2/3 of the total stake. What this gives us, the checkpoint B has enough votes to be justified. So through a kind of quite weak assumption, this checkpoint of block B will be justified over the next epoch. And then because we know that every honest validator only votes for a descendant of B, if there is any checkpoint in a future epoch which will be justified, that for sure will be a descendant of B, which means that B will never be filtered out and therefore will be canonical forever. Just going through some initial experimental results that are due to Circle, so thank you, Circle, for running them. There is a blog post actually coming out soon, so stay tuned. The setup was they ran the confirmation rule over 6 days. They detected over these 6 days 56 blocks that were reorged. Some also were 2-block reorgs. The implementation was a proof of concept. There were some approximations. So for example, they were polling beacon nodes every 10 seconds rather than running the confirmation rule at the beginning of each slot. Also, they were estimating the FFG weight using just the LMD weight. However, the results are very encouraging. First of all, none of the reorgs were ever confirmed, no matter the value of beta. So this gives quite good confidence of the security provided by this rule. Second, in terms of performance, what they saw was that if you fix beta to be around 20% of the stake, you could see confirmation in 4 or 5 slots. If you go up to 30%, you get to 8, 9 slots. However, we think, this has to be proved in practice, that if the rule is implemented by running it at the beginning of a slot, then we should be able to confirm a block in 12 seconds. So this leads me to the last slide. So if you are interested in testing this and you're interested in implementing this confirmation rule on a beacon node, reach out to us. Our contacts are in the talks description. Also, one is the QR code for the paper, which is also linked to the talks description. And the second QR code is to the Ethereum consensus spec PR, if you are interested. That's all. Thank you.
Okay, cool. I'm going to approach from behind and push you towards the middle as we address questions. So we'll start from the top. Seems like confirmation rule will get obsolete with single slot finality. Does it make sense to work on it at this time?
Seems a question we asked ourselves.
Yeah, the point is that we still don't know exactly when single slot finality will come out. And the confirmation rule is something that we already have. So it can already be helpful in some sense while waiting for single slot finality. But yes, once single slot finality will be out, probably there will not be, it's not needed anymore. But yeah.
Also, it's not, say, it's, in our opinion, not too difficult. Doesn't require any hard fork. It's not that difficult to, I wouldn't be the one implementing it, but I don't think it's that difficult to implement, or wouldn't take that long, and provides good benefit in the meantime, yeah.
Okay, cool. The UI is not updating. How do you estimate beta? Is it a new parameter?
It's user subjective belief on the value of beta. So the user picks their beta that they believe that is the maximum, and they query. And according to what they believe is, they get the result accordingly.
Well, can a confirmed transaction still be affected by a reorg?
So this, as I said, one of the assumptions is that votes are delivered by the end of the slot. If there is a network partitioning, this is not true anymore. Yes, it can be affected by reorg. So it's not as safe as finality, but it's quicker. It's a sort of trade-off.
What is the recommended value of beta you suggest? Is it 0.2, and how does it impact security?
That's a very good question. Of course, beta cannot be larger than 30%. In other aspects, and some, for example, that work on EPBS that's been researched out, usually 20% tend to be what people are comfortable with in setting beta, so that seems like a good, reasonable value.
What are the security guarantees? Do you have any probabilistic assumptions?
We have some probabilistic assumptions, which is the one that said, we have this assumption saying we take any sequence of slots and the maximum beta of the stake is dishonest. As you know, the committee is sampled randomly. And so when you cross actually the epoch, you have some also probability measure that if you assume that, over the entire stake, say beta 1 is dishonest, the fact that over some set of committee this is less than beta is a probabilistic measure, but it goes, the probability goes up very sharply. So it's, yeah, there is some probability in there from that perspective, yeah.
Can you explain validators' honesty scoring more?
I'm not sure I fully understand the question.
If not, we can move on, and whoever asked the question can, I guess, re-clarify. And we have, the example has an honest amount of validators quite optimistic. What about a more pessimistic scenario? Can validators be honest most of the time until they find something they vote adversarial?
Okay, that's right. If I understand the question correctly, I mean, if this is the behavior you're thinking about, that should be accounted in the beta. So this rule relies on belief that 1 minus beta, they're honest and they will vote according to the rule. If some point, if in the future some of them become dishonest,